All right, let's go ahead and get started. This is lecture number 22, Wireless Communications Lab. So today we are going to talk about the probability of error analysis in Rayleigh Fading channels. And so I'll define what I mean by Rayleigh Fading channel and also how we define probability of error here. And the main thing is that you should be able to calculate a bound on the probability of symbol error that we do in class here. So there's a couple of tricks associated with that calculation. So that's one of the main things that you should get out of the lecture here. And then the second part, which will probably be less than half, will be to talk about this concept of diversity. So what we're going to see is that communication in that Rayleigh Fading channel is very impaired. It's not very good. And so diversity is going to be a technique that we can use to mitigate to some extent the effects of fading. So we'll talk about the different techniques, in particular just sources of diversity. Now actually, I don't think we'll have time to derive the benefits of those effects, so that we'll do next week. And we'll look at, in particular, focusing on spatial diversity. So that's the plan here. Now, let's go through a quick review here of what we did on Monday here. So on Monday, we talked about these notions of small-scale fading region. And so we drew this quadrant chart here. And so I reproduced it up here. The main things are that on one axis here we had signal bandwidth, and then this is like small and large. And the other axis here we had what I was putting symbol time, but is really more practically frame time. So I've put like frame time up here, and this is small frame time and large. And then the crosshairs here are defined by these quantities that we computed. One is the coherence bandwidth, and the other is the coherence time. And so remember that the coherence bandwidth was inversely proportional to the RMS delay spread, and that this quantity is a function of the spread in the time of arrivals of the different multipath components in the wireless channel. And the significance of those is a function of the bandwidth of the channel, or equivalently how small the symbol period is. You know, so if a symbol period is small relative to the durations of those different multipath components, then you equivalently have high bandwidth, and you end up in this frequency selective case here. So let me look at this here. Small. Sorry, I think I labeled this wrong here. It should be large here. And then the time over here, so coherence time. So your coherence time is, roughly speaking, the time in which the channel is constant here. Now, we defined it based on the Doppler spectrum, in particular the maximum Doppler frequency here, which is a function of the mobility in the environment here. So the higher the mobility in the environment, the maximum mobility, the smaller the time that the channel remains roughly constant. And so if your frame time is very small, it easily fits within that coherence time, and you can treat the channel as being roughly constant. And if the frame time is too big, then the channel might change during that transmission. And so then we say that, you know, there's going to be fast fading. And so in terms of coherence time, we have either slow fading or fast fading. In coherence bandwidth, we either have frequency selective or frequency flat. And then last time, we also talked about the equivalent signal models that arise in each of these different quadrants here. So remember the different signal processing models. We had the frequency flat channel, the frequency selective channel, the time-varying flat channel, and the time-varying selective channel. And each of those leads to different types of algorithms that you need to implement, different sorts of equalization, different kinds of mitigation here. So what we're going to do today is we're going to focus on the, specifically on the case of frequency flat and slow fading here. And so let me just highlight that right here. And we're going to focus on this case because what we want to do today, which is really different than what we've been doing so far, is we want to do some analysis of performance in this particular type of a channel here. And this happens to be the easiest channel on which we can do some performance analysis, and it's good to give us some intuition about system performance here. So I'll explain that now here. Okay, so this is going to be probability of error analysis. And so what we want to do is we want to, in general, as wireless communication engineers, we want to evaluate the system performance in different propagation channels. Because we have to design systems that, are robust and work well in a variety of environments here. Now, from the perspective of the lab, you're getting the view of, wireless engineer from the perspective of someone who's doing like a lot of prototyping. And so if you wanted to evaluate performance in different channels, what you would reasonably do would be to move the equipment around, go to another room, change the antenna locations, and, try it out. See, did I get any errors or not? And that's perfectly reasonable. Now, often we're designing very complex systems, and we often design the system before we actually prototype it. It's typical, right? Because normally you try to figure out how you're going to make the system, make some design decisions, and then you see how it works. Because usually building the prototype is much harder than writing things on paper. So what we want to do is we want to get some insight into how the system works before we get to the step of prototyping it here. And so a key step here is this idea of the channel model. So we want to determine performance in propagation channel, but which one? Do we pick one channel, another channel? How do we determine those channel coefficients here? And so there's a whole area of inquiry, which is all about channel modeling here. And that's essentially concerned with building mathematical models of the, propagation environment for system evaluation. And in this class, when I'm talking about system evaluation, I'm going to mean in particular the probability of error. That if you take some of the other wireless classes, you'll see that we use other metrics of performance. There's throughput and goodput and capacity and rate and other interesting quantities here. The channel modeling itself, it's a broad field, and it is certainly inspired by measurements that have been made. Now, I'm going to give just a brief taxonomy here of some different kinds of models, because there's a lot of different ways to model the channel, and to some extent the approach that you take is kind of biased based on your background here. So I'll start off with the two ways that I like to classify. The first is stochastic models, and the second is deterministic models. So I'll explain each of these. I'll start off with the deterministic model here. So deterministic model is something that you might use if you're doing ray tracing, for example. You have an electromagnetic model of an environment, you place a transmitter and receiver, you compute the paths between the transmitter and receiver, you get a whole bunch of impulses with delays. This looks just like what we did, you know, on the order of lecture 3, 4, or 5. We derived equivalent channel. You know, so we start off with this deterministic approach, use the environment. You know, you start off by saying, well, I want to model this time-varying impulse response, but you know, I'm going to model it only a certain period of time, so I'm going to consider linear time invariant system, and then we derived the complex baseband equivalent channel, and then from that, the corresponding discrete time impulse response here, and then given that impulse response, you might implement that in your system simulator and perform some simulations. And so this piece over here, we kind of determine from the environment, for example, ray tracing. And we did examples of this in class where we had one path, and also on the homework where we had two paths. You know, so we had like a reflected path here, and we modeled this h of tau as some sort of an alpha delta of t minus tau 1 plus beta delta of t minus tau 2 here. You know, and then we band limited that, converted it to baseband, sampled it, and got our discrete time model here. And this is, you know, is a reasonable approach here. The challenge, though, is that you have to have, you know, some sort of a good model of the environment here, and something that's representative of the place that you're going to use this here. Now, we have in the past at UT here developed, we used to have an electromagnetic model of downtown Austin before all of the condos were built, so it was admittedly a bit lower complexity than nowadays here. And yeah, so we used to do some experiments where you could pretend to be driving in downtown Austin and, you know, computing this kind of impulse response and evaluating performance here. So that's possible here, and that does leverage, you know, having a complete system to do simulations here, but also that requires that you've already done a lot of thinking about how the system is going to work. So it's more, to me, this approach is closer to prototyping than it is to this early system design. So this other approach is a stochastic approach, where instead of trying to, you know, calculate this impulse response from an environment, we say, well, it's going to be some, you know, realization of some sort of a random process. So I'm just going to write this like, you know, roughly speaking like this here. So we're going to generate channel coefficients according to some distribution. And we might, depending on the kind of simulation that we're working on, we might, this actually might be a random process, it might be correlated over time, it might be independent. But the key thing here is that we're going to evaluate performance over different realizations of the channel here. And so you could take this same kind of philosophy here, and then you could generate, you know, realizations of the channel, perform a whole bunch of simulations, and then compute your favorite performance metric here. So for example, you know, these simulations might lead to what we're going to do today, probability of symbol error. Now, what we're going to see is that depending on what assumptions you make about this, this channel's distribution, that we're going to be able to bypass the simulation step and go straight to the probability of error, or some bound on the probability of error, using an analytical technique. And so that's what I'm going to provide you with today, is an example of an analytical technique. And so a benefit is going to be that we're going to get some relationship between the probability of error and the parameters of this random process, and we won't have to do any simulations. And so then the idea would be that we can say, okay, you know, this kind of modulation works this well in this particular channel without actually having to try it out. And so then we can, you know, make decisions based on those results there. So that's what we're going to do, is we're going to take an analytical approach. And the drawback of the analytical approach is that, you know, to get nice, clean expressions, we generally need to make some really simplifying assumptions on the channel, and we also have to make simplifying assumptions on the system. So it's not going to be as complicated as if you potentially can do simulations. With simulations, you can implement the effects of training, synchronization error, different kinds of noise, and so on here. So this is it's a compromise in this whole design space here. So we're going to focus on, we've kind of dealt with this already at the earlier part of the class. Now we're going to focus on sort of this analytical characterization here. So any questions on just the modeling philosophy here? Okay, we'll keep going here. So now, to perform this performance evaluation, what we're going to do is we're going to look at the frequency flat, slow fading channel. So this is that one quadrant that I just mentioned here. And so for purposes of doing this evaluation, we're going to write the input-output relationship slightly differently than we've been writing it before. We're going to write it like, so normally we have the y of n, our synchronization, everything is all done perfectly here. I'm going to factor out the square root of ex, which often I remove, because from a signal processing perspective, we don't really need it. But to do performance analysis, it's convenient to have factored it out here. And so I'm going to write the input-output relationship like this, where this is the usual additive white Gaussian noise. This is our symbol. This is our complex channel coefficient. And this is just the square root of Ex scales the transmit power. So in the work that we did a couple lectures ago, we were always just incorporating this Ex into the H here. So now I'm just factoring it out because I want to pull this out in the performance expressions here. So this is a very simple model. We can extend, and you might do one of these extensions on the homework here. It can be extended to include large-scale fading, right? Distant-dependent path loss. That's not here right now. So we could extend it to include that. There are also extensions for frequency-selective channels. The difficulty with frequency-selective channels is that we need other probability of error expressions, and we didn't derive those in the class. So that's harder for us to do, but it's possible. And if you take other classes, you might look at some of those extensions. And we can do things like incorporate channel estimation error and other practical impairments here. But we're going to start with this simple model here. Now, before getting into the actual calculations, I want to explain something about how we're going to be thinking about this, this channel here as a random variable here. So what we're going to do is we're going to, and you can think about it that we're going to communicate over different realizations of the channel. And so you could imagine that we have this is what's called a block fading model here, but so suppose that we communicate over different channel realizations. And so what I mean is that we're gonna take information and we're gonna package it up together in a frame, like we do in the lab here. This maybe is 100 symbols. And all those 100 symbols will see, let's say, channel H1. And then, at some time later, we'll send some more symbols that will experience channel H2, and so on here. And so we are imagining that the channel is constant during this block here, but is changing from block to block. And this corresponds to us having frames that are small relative to the coherence time, but each time we send a frame is perhaps, the time difference there is perhaps larger relative to the coherence time. So, you know, in an extreme case, each of these could see sort of an independent realization of the channel here. So we're going to capture this variation by treating the H. I mean, we could generally write this as a random process, but we're going to capture this variation simply by treating H as a random variable here. So instead of like putting in the time index, we actually only need to consider it to be a random variable. So we're going to treat okay, so now at this point here, to do any kind of analysis, we need to specify, you know, the distribution of this random variable. I mean, so we can do something with it. And like everything else, there's several different options here. The one that we always start with from an analytical perspective is what's called Rayleigh Fading. And so you hear the term Rayleigh Fading channel used a lot. And so we're going to evaluate performance in the Rayleigh Fading channel. So what that means is very specific. It means that the channel H has distribution, complex Gaussian with zero mean and unit variance here. Now, typical, you know, thought process here, at least like when I first saw this, was, you know, why are we not calling this Gaussian fading? Because it looks like a Gaussian random variable, which indeed it is. Well, I think the reason is that we also have Gaussian noise here. So remember that when we did initially performance evaluation, we just had y equals s of n plus v of n. We called that the Gaussian channel. So we already used Gaussian channel for Gaussian noise. So I think that's why we don't call this Gaussian fading. It's just a little bit of confusion here. Now, Rayleigh fading does actually have a meaning, though. And it turns out that if you compute the distribution of the magnitude of this complex variable, and that distribution has a name, and it's called Rayleigh. So in statistics, if you go look up, you'll see that there's a Rayleigh distribution, and it turns out the magnitude of a complex normal 0, 1 random variable has the Rayleigh distribution here. So that's actually where the name comes from. It's the envelope of the fading. It's not the distribution of the fading itself. Now, just for sake of completeness here, the magnitude squared also has a name. Remember, the magnitude squared here would be the sum squared of two independent Gaussian random variables here, each with variance 1/2, and that is actually scaled, but it's essentially a chi-squared random variable with 2 degrees of freedom. Now, in the class here, we're only going to exploit this fact here, that the channel has this Gaussian distribution. But the results that we're deriving, you could derive them in an alternate way by using these other facts here. And so, you know, sometimes you have to be flexible in a problem and think, you know, it may be better to work with a different distribution, which is equivalent to just like a change of variables, in my opinion here. So, but we're just going to focus on this one here. Okay, so now let's, before we get to the calculation here, I want to say something about, you know, perhaps why Rayleigh fading is not just such a crazy idea. I mean, it does seem like we're just sort of pulling this out of thin air here. The typical motivation for having like a Rayleigh type distribution is, so consider a transmitter and a receiver here. We assume that we're operating in what's called the rich scattering environment. So rich scattering means that there's a lot of multipaths coming in, all different directions here. And because we're assuming that the system is frequency flat, the time durations between these multipaths all very small. So that doesn't create any intersymbol interference. So what's happening, though, is that each of these paths here has a slightly different path length and thus phase, and each is also scattering off of a different object, and depending on, you know, the angle of incidence, the permeability, and all those other good things, there's going to be a certain amount of that signal that's attenuated here. So essentially, you have a superposition of a whole bunch of different signals coming in with slightly different phases and slightly different amplitudes. And if you thought about those as being like independent random variables, then you could say that, well, I'm summing up a bunch of independent random variables and taking the limit here, using the central limit theorem, we get something that looks like a Gaussian distribution. So that's sort of the motivation here. So just to write that down here, so we have many signals adding with different amplitudes and phases. And so then you could say that, well, this sort of goes to, Gaussian distribution here by the central limit theorem. Now, of course, you can, make that more precise if we make assumptions about what the channel looks like here. So this is not a proof. I'm just giving you kind of the intuitive argument about why it seems to make sense here. And the places where it wouldn't make sense would be places you don't have a lot of scattering. So satellite to satellite communication, free space, aside from the junk floating around, there's not a lot of reflections. And so Rayleigh fading wouldn't make a lot of sense. Receiving in this room, we do have a lot of scatters, might be okay. So that's just giving you some intuition here. So with that, actually I forgot, I wanted to say one other thing here, which is that there are some other related distributions to Rayleigh. The one that's most closely related, and we might see this one in the homework, is the case where instead of having zero mean, you have a mean. And the variance might be 1, or the variance might be something else here. This channel has a name, it's called the Rayleigh distribution. Because the envelope has the Rayleigh distribution, so it's called the Rayleigh channel. And this is used when there's a strong line of sight component. And that line of sight component is signified by having a non-zero mean here. So if you had a system where you had like a direct path here from transmitter to receiver, and then a whole bunch of reflected paths, then you might instead use this Rayleigh type distribution here. So that's also used in the literature, leads to more complicated expressions. So we're going to stick with the Rayleigh fading result here. All right, any questions on that? Why is the envelope, or? Yeah. Okay, so we'll see that in a second here, but essentially, if you remember, when we derived the SNR for a system where we had something like this, y of n equals alpha s of n plus v of n. And so we derived the SNR of that when we were looking at the maximum likelihood detection. We found that the SNR was something like this here. So the system performance was fully determined by the magnitude squared of that alpha here. So the magnitude is the envelope. Magnitude squared is the power. So that's maybe the main reason. Essentially, we don't care about the phase. And then depending on if you want to think about this as some random variable squared or just some random variable, you can look at it either its envelope or its power, which would be the magnitude squared. Any other questions here? All right, so we are going to take one short break here because the next derivation is somewhat long here. So I have spent a fair amount of time trying to follow up the discussion we had on Monday about the wireless cockroach. And that was just awesome. There's no way I could find anything better than that, at least today. So I decided to come back to something else that's, I apologize if it's not as exciting here. But I was looking on the, and I don't expect you to read this here, but this RCR wireless webpage, which is one of the places that you can go for wireless news, and some of the articles that I show you come from there. There's an article by William Ho, who's a venture capitalist here. And the thing that I wanted to highlight here was that this article is about the importance of spectrum below 1 gigahertz for cellular. And so I wanted to highlight this point here that, industry veterans understand that the low-band spectrum's propagation characteristics provide greater geographic reach and coverage and better in-building penetration relative to higher frequencies here. And so this is, you can think about this here as being like a basic result of just the first free space equation that we talked about here, that the lower the frequency, the larger the average received power here. And so, I think that makes everyone in the class now an industry veteran, now that you understand that, lower frequency signals, can more easily propagate further away here. One thing also I wanted to mention here is that we haven't talked much about penetration, like loss. All of our path loss models really are designed for sort of outdoor, the ones that we were talking about here, but lower frequencies also tend to propagate better indoors too. And so, this was just essentially an article that was saying that, oh yeah, by the way, only 2 of the 4 cellular providers in the US have a lot of frequency spectrum below 1 gigahertz. And because of that, they're going to have some advantage in the future. So that's what the article is about. But I just, picked this out here. I thought that was interesting here. Anyone have any comments or questions on that? So connecting this back to the wireless cockroach story, if you had lower frequency, you could control your cockroach at a further distance. That's the connection there. If you weren't here on Monday, I apologize for the. You have to check out this. Just Google like wireless cockroach, and BBC, and you'll get this article. It's really nice. Yeah, and this is a figure here where you can't see the carrier names, but these are 2 U.S. carriers, and this is a third. And these guys have a lot of low frequency spectrum, and this carrier, unfortunately, has almost none. Oops. And so the benefit of having this lower frequency also is that if you're serving an area that's not very populated, because the signal propagates further, you can put up fewer base stations. So if you're covering like West Texas, where the population density is lower, you can get by with, say, 1/4 of the infrastructure if you have lower frequency. And that means a lot less cost. So that's, Anyway, some insight you can get from propagation modeling. Anyone have any comments on this? No comments. All right, good. You're making me look really good here. All right. So with that, we go back to computing the probability of error here. So let's go for, slide 4 here. Okay, so the main activity for today here. So we're going to compute this bound on the average probability of symbol error. And so we're going to start from this, again, the system model, y equals square root of Ex, H S of n plus V of n here. Now we know from when we derived the probability of symbol error for the Rayleigh Fading channel, probability of symbol error for the additive white Gaussian noise channel. So we derived a bound, which was the union bound here. Now, if I know this is a random variable h. If I know this channel here, so I'm going to write this as probability of error Ex over n naught. That's our SNR that we always have with additive white Gaussian noise channel. I'm going to condition on knowing that value of h here. And so using the results from, maybe 10 lectures ago now, we had this union bound that was a function of the size of the constellation times this big Q function here we had S and R d min squared over 2. And then this here is just another amplitude, so that just shows up here as amplitude squared here. So this was our, flexible bound for the probability of error, and we talked about, I also had presented the exact expressions for QAM systems, which are a little bit more complicated and also harder to do the calculation for today. So what we can see from this picture here is that, having a channel realization that's large is good, because that gives us effectively, higher effective SNR, and having a small value of the channel here is bad. So the small values of the channel we call fades. So if the channel is very small, we call that a deep fade. And so if you get stuck in a deep fade, your probability of error ends up being very low. That's bad. So the probability of error, if we're modeling this h here as a random variable, is also a random variable here, because it's going to vary, right? So we're conditioning on h, but this h is random here. So depending on the realization of h, we get a different quantity here. So there's different things that we could compute. The most standard quantity of interest is the average probability of error, where we're going to take the expectation with respect to h of this conditional probability of error here. And so here's where the distribution of the channel comes in. Right here, no distribution of the channel, because we're just conditioning, treating it as, as given. And now here, we have to plug in our assumptions about the channel distribution here. Now, so looking at this bound here, we can take the expectation here on the other side too. And so that gives us, this is less than or equal to n minus 1 times the expectation of this q square root of ex over n naught d min squared over 2 times magnitude squared of h here. So what we're going to do now is we're going to focus on calculating just this expectation here. And that's kind of a hairy-looking task, as you can imagine here, because remember this q is this Gaussian error function here. So we're integrating over the tail of the Gaussian distribution here. You could actually plug that in and do some interesting tricks and come up with an answer there. That's a bit more complicated than what we're going to do. So what we're going to do is we're going to further upper bound this quantity here by using this result that the q of x is less than or equal to e to the minus x squared over 2. You can also put 1/2 in here, it's fine. This is the Chernoff bound. And we also talked about that when we talked about the probability of error evaluation here. So we're going to substitute this in here, and we're going to get an upper bound on our upper bound here. So this is going to be expectation of probability of error. It's going to be less than or equal to, I'm getting rid of the n minus 1 here, so it's going to be less than or equal to expectation of e to the minus that argument squared. So what we had before was this right here, this squared here. So we need to take this thing here and square it and divide by 2. So we can just copy this over here. So we're going to get e to the ex over n naught. Instead of 2, I'm going to put 4. And then we have magnitude squared of h here. Now, if you have been studying probability quite a bit, at this point you could almost stop and leverage the moment generating function. Or if you don't know that, we can apply this trick here. So what I'm going to do is I'm going to take the expectation of this e to the stuff here times modulus of h squared. What I'm going to do is I'm going to write out this expectation. So remember that for these complex, circularly symmetric complex Gaussian distributions, we can write this out in our usual integral form. So I'm going to bring this over here. remember, I'm writing equal here, so this just means this quantity is equal to the right-hand side of this here. So this is equal to this integration of e to the minus ex over n naught d min squared over 4 magnitude squared of h. Now we have to write the distribution of complex normal 0, 1. So that's going to be 1 over pi e to the minus magnitude squared of h, and then have this dh of here. And so just remember that this was that complex normal distribution here, right here. And so this trick now that I'm going to show you here, and I'm showing you this trick, first of all, I just think it's cool, and second, because we're going to use this trick when we derive the probability of error for the case of spatial diversity. So we're going to actually derive something for receive diversity and for transit diversity when we talk about multiple antennas, which will be next week. So we'll use an extension of this trick that has a similar flavor here. So the basic idea is that we want to exploit the fact that a distribution function has to integrate to 1. That's the core idea we want to exploit here. Now what we do here is we look at this and we see that, well, I've got a magnitude h here. I've got one here. So conceivably I can simplify this together to get 1 e to the something that's a function of magnitude h. And if I can rewrite that, maybe I can make it look like a Gaussian distribution. So that's what we're going to do here. So first of all, we're going to simplify this. So I'm going to put the 1 over pi here. So 1 over pi. And then I'm going to combine these together. So this is going to be e to the minus magnitude of h times, this is going to be 1 plus, and then we have this stuff over here, ex over n naught d min squared over 4 here. And now, this almost looks like complex Gaussian distribution here, except that, the variance term, which we'd expect to be in the numerator, is sitting up here. So we're going to rewrite that as 1 over pi. I'm deliberately leaving a space here that I will fill in a moment here. E to the minus magnitude of h squared divided by 1 plus ex over n naught d min squared over 4 inverse here. Now, if this were a complex Gaussian distribution with some non-unit variance here, we would have something like this here. We'd have like 1 over pi sigma squared e to the minus something like this here. So we'd have a sigma squared here and a sigma squared here. And remember, this is not sigma because it's the complex Gaussian distribution here. So what I'm going to do is I'm going to create a sigma over here in the denominator here. I'm going to just go ahead and stick that in. That's my sigma. So you get 1 plus ex over n naught d min squared over 4 inverse. And so that I'm not, adding or subtracting anything, I'm also going to put it here on the numerator. Here. And now, what I can do here is I can see that this quantity here this is essentially probably a distribution function for a complex normal random variable, 0 mean, invariance 1 plus ex over n naught, d min squared over 4 inverse here. And this is just a constant, so I can pull it out. So then I can, the point here is that the integral over all h here, this thing integrates to 1, so I'm left with 1 plus ex over n naught d min squared 4 inverse, which is just 1 over ex over n naught d min squared over 4 plus 1. And so now that I have this result here, I can plug it in into my original expression here. And so I can write that the probability of error, the Rayleigh Fading channel, less than or equal to n minus 1 divided by Ex over n naught d min squared over 4 plus 1. And then to get some intuition from this, we can look at high SNR. So high SNR, this quantity here will be a lot bigger than 1. And so we can neglect the 1. And so I'm going to write like a, little tilde here as this is kind of like a high SNR approximation here. This is going to be n minus 1 over Ex over n naught d min squared over 4 here. And notice that this right here is essentially just proportional to the inverse of the SNR. Now, the significance of that, that's the result here. Now, to get a sense of the potential severity of this, recall that for the additive white Gaussian noise channel without any fading, we had this Ex d min squared over 2n naught was proportional to e to the minus Ex over 4n naught d min squared here. So in the Gaussian channel, this probability of error is decaying exponentially in SNR. And here it's decaying linearly. So that means that the probability of error gets small much faster in the absence of fading than it does with fading. Now, to get a better sense of this, let's look at a plot of the probability of error. All right, so I'm going to color this one here pink. Occurs to me I should have printed this in color here. I've been printing in toner save mode to make my color cartridges last here. All right, so this is an example of the probability of symbol error for binary phase shift keying, BPSK. And because there's only 1 bit per symbol, it's also the probability of bit error. And then this is the SNR down here, which is Ex over n naught. And then this is the probability of error for our flat fading Rayleigh fading channel. Now, to be fair, I've plotted the exact probability of error, not the bound that we computed. But if we were to plot the bound, I'm sorry I don't have it here, it would look something like this. Here. So at high SNR, it has the same slope. And at low SNR, the probability of error actually becomes greater than 1. And you all have plotted the union bound before, and you know that it's very loose at low SNR. So you see the same effect too here. So the bound that we plotted, it turns out, is usually is good at reasonable levels of SNR here, which in this case is a few dB here. And the offset is usually on the order of a couple dB. So the thing to get here is that, so here's now remember, this is SNR in dB, it's a log scale, and this is also semi-log y, like we always plot the probability of symbol error here. So it's like kind of like a log-log plot here. And because it's log-log here, so effectively what we see here, here you can see this kind of exponential decay here in log-log case here. So you see the decay with SNR, and here you see this kind of linear behavior here. Now, in terms of performance, so typically we design a communication system to operate at some target probability of error because we can't get 0. And we're going to use error control coding on the outside to clean up some of those errors. And so depending on the kind of code that we use, we target a certain probability of error. So let's say that we are targeting 10 to the minus 2 here. So that means we're allowing one error out of every 100 symbols here. And if we had an additive white Gaussian noise channel, we would require a little more than 4 dB of SNR to achieve that. Now, if we're communicating in the Rayleigh Fading channel, we need about 14 dB. So this means that you need, if you want to maintain this same probability of error, you would need 10 dB more power here. I mean, you can't really, okay, you could squeeze the noise a little bit by building better circuit components, but an easier way to get this big gap here would be more transmit power here. So you'd go from 0 dBm to 10 dBm. Big jump, 10 times the power in the linear scale here. So this gap here, this is what's called the fade margin. And so the fade margin is essentially the extra amount of, you can think about this as the extra amount of power that you have to spend to achieve the same probability of error as in a Gaussian channel in your fading channel here. So that's the fade margin there. And what we'll see is that, so the problem here is that this gap is big. And this is only for BPSK. Now, if we were to plot this out for 64 QAM, the curves would shift, and the probability of symbol error would be similar, but the probability of bit error would have to go even lower, and the gap can be even bigger. So the problem here is that this is quite big. Now, we'll do an example. I think this is one we do in the homework here, where, so last time we looked at the range in the presence of large-scale fading. So we computed the probability that you had sufficient coverage as a function of distance, giving a certain distribution here. And so if you add on top of that the small-scale fading margin, what it means is that you have to pay another 10 dB penalty here to communicate in the fading channel. So it means that you can't communicate as far away, because at the edge of the cell where you're communicating, there's a likelihood that the channel gets very small there. So you can't communicate effectively there. So you have to come in closer. So another way to think about this fade margin is going to be the reduction in path loss that your system can support. So you can't go as far. Range is reduced. Now, as a preview of what we'll do on Monday, and we'll talk about today, there's a way to shift this curve over. And we can do that using a concept called diversity here. So that's what I'll summarize right now. But effectively, using some other interesting tricks, we can obtain curves that still end up being flat, but will actually get closer and closer to the Gaussian case here. And this is achieved through what's called diversity here. And so we'll see that diversity reduces the fade margin. So we'll calculate that on Monday, but we'll see the performance. We'll study the different techniques right now for diversity here. Okay, so any questions on this here? So again, the main summary here is, first is to be able to calculate this bound on the probability of error. You have to define Rayleigh fading, and then you should be able to evaluate their performance, compute the fade margin at a given target probability of error, and then we'll combine this with some of the other large-scale calculations. And that's going to be what's called link budget analysis, which we do I think we do that next Wednesday. Okay, any other questions here? Like, no questions? Okay. Okay, so let's talk a little bit here about diversity. Okay, so diversity is a very powerful concept, and it's a concept that's used not just in wireless communications, but I mean it shows up in biology and many other facets of life here. So essentially, the idea is that diversity is a means to overcome the effects of fading by providing multiple means for the signal to get from the transmitter to the receiver. So at the core, this is what diversity means to us as like wireless communication engineers. Now, diversity, where it shows up in other places, has anyone plotted something with like directions with Google Maps, for example? It gives you like choice of 3 routes. Well, what if your preferred route has a traffic accident? You could take an alternate route here. If you're going somewhere where there's only one road and there's an accident, you're stuck. So diversity we see in terms of transportation as there being a whole lot of different alternatives from getting from one place to the other. Now that setup is a little more complicated because there's other people also driving on said roads, and so they may also realize that, and so, that's a little different concept than here. But it's basically just multiple alternatives here. So from a fading perspective, if we have a very deep fade on between our transmitter and receiver, that's really bad. But if we have maybe 2 paths, the likelihood, if those 2 paths are somewhat independent, the likelihood that there's fades on both of those paths tends to be much, much lower than on either of the paths here. So it's kind of a reliability concept there. And so the more possible alternatives you have, the more likely it is at least one of them is good. Now again, this is a concept, I'm explaining it to you at a high level, and we'll calculate this on Monday, and we'll derive more precisely how this affects the probability of error. But that's kind of the intuition. So it's a means to get multiple different versions of the same signal that have experienced different channels. So then the question now is, how do we get this? How do we find this in wireless here? The place to look is actually back at that plot in terms of coherence bandwidth, and coherence time. Because the coherence is giving us an idea about how long it takes for the channel to decorrelate in some dimension. So let's look at an example here, which is what's called time diversity. So time diversity, so suppose that I have a flat fading channel. I'm going to plot it just for ease of plotting in terms of continuous time here. So let's look at like one realization of this channel here. So it goes, so it looks, something like this here. And we had this concept that we computed called the coherence time, which was telling us roughly how long you have to go until the channel is decorrelated here. So it doesn't tell you that the channels are absolutely different, but it tells you on average that they're reasonably different here. And so the coherence time might be, something like this here, for example. And so the idea of time diversity would be to try to send information, the same information, at multiple points in time. So I might send something here and I might send something here. And then later I might send a new data packet here and then resend it here. And then, send packet here, send packet here. And what you can see, hopefully you can see the color here, is that, the red one The first one was a little bit better, not a huge difference. The green, you know, the second transmission time was a lot worse than the first, and the purple, also the second was a lot worse than the first here. So by sending this twice, I've seen two different parts of the channel here. And if I space these opportunities far enough apart, with high probability I'll see different you know, potentially different fading levels there. So they'll be roughly independent, and hopefully they both won't be bad. It's possible that they're both bad. But that's like the idea here. So we're going to send information multiple places here as a function of the coherence time. And so that's the idea here. So maybe just write it down, is spread information or symbols across multiple coherence times. So there's actually several different ways to do this. Sort of a simple approach would be what's called repetition coding, where we literally just send it again. So send the information twice. That is a perfectly legitimate way to get diversity. You can usually do better, though, with something a little bit smarter here. But that's reasonable. There is a trickier approach that you could use. So repetition coding, not widely used because you can usually do something better. There's a slightly trickier approach, which is called retransmission. This is a layer 2 function. It's not something we usually talk about in class. The retransmission idea would be that the receiver would ask the transmitter to send the packet again. You know, it tries to decode the packet. It realizes it fails. The channel's in a fade, so it says, hey, transmitter, can you send it to me again? And the idea would be that perhaps by the time the transmitter gets around to sending it again, the channel has changed, and maybe it goes through this time. So that's a way to get retransmission. The nice thing there is that, you know, like here, if the channel's good, you just send the data through. Here it's good, here it's good, here it's good. Oh, it's getting bad now. Maybe we do some retransmissions. Oh, we retransmit, it's still bad again, but eventually it gets better. So retransmission, in some sense, is more efficient. Doesn't use as much overhead. But it's a higher layer function. And there's other trade-offs associated with that. The way that is most common in wireless systems is what's called coding and interleaving. So this is error control coding combined with the interleaving operation. So we saw this both in 802.11a and in the GSM system. We talked about that in both cases there. And so, for example, in GSM, I don't remember if I talked about the interleaver depth in GSM, but in GSM, speech packets are encoded over either 4 or 8 bursts, depending on exactly which codec mode you're operating in. And most information is encoded over 4 or 8 bursts. So it uses coding and interleaving over 4 or 8 bursts for almost everything. I mean, there's the broadcast control channel doesn't do that, but almost every other control channel does here. You know, and so then you have information is spread over these 4 or 8 different opportunities here. So what this would be like here, going back to this example here, this would be like I take my information and I send part of it here, 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 part of it here. But because of the redundancy I've added from the error control coding, I can correct some of the errors. So perhaps I can correct the errors due to the fading down here. Now, if too many of them got stuck in a fade, it would still be lost here. So you get a little bit of resilience there. And actually proving how much how much benefit you get from resilience to fading is actually challenging with coding and interleaving. But it is actually very common. Now, the one, I should say, like, you know, I don't know if it's a disadvantage or the one aspect of exploiting temporal diversity, time diversity that's important is that you need Doppler. right? Because Doppler is what gives us a small coherence time. If we're operating indoors, the channel's fading very slowly. Let's say it's fading on the order of, coherence times on the order of seconds. That means that we would have to, send our data now, send it again a few seconds later to exploit that. Too long, and in systems like speech, systems like cellular, where you have to decode that packet in on the order of, let's say, 250 milliseconds, you can't spread too long there. So actually even 120 milliseconds is long. So you have to have a fair amount of variation in the channel. So this concept doesn't work in some systems. It works in some, but not others. In cellular, this would work if you're traveling by car or bus or train, but maybe not at pedestrian speeds. So time diversity is good, it works, but it's not always there. So let's look at some other techniques here. So this is the one that's this is commonly used, but it's not always available. So another approach is frequency diversity. So frequency diversity actually comes from transmitting information with a bandwidth larger than the coherence bandwidth. Equivalently, the symbol period is on the order of or smaller than the RMS delay spread. So what this means is that, so if we looked at the transmitter and receiver here, so we talked about this idea of a power delay profile. And let me plot it here, assuming like a 3-path channel here. So this is like my power delay profile here, and these are the average values of the paths here, and then these are the differences in delay here. So this might be tau 2 minus tau 1, tau 3 minus tau 1 here. Now, if we have a large enough bandwidth or a small enough symbol period, then each of these paths here deliver information at different points of time here. And these paths themselves are actually different ways for the transmitter to get to the receiver. So intuitively, if I have a direct path here, a truck comes and blocks it, there's still signal reflecting off of, say, a building here and a building here. And I can exploit this if I have a large enough bandwidth, because otherwise these are all adding up together with slightly different phase and amplitude, so they're just going to create a different fade. But if they're coming at different points in time, potentially I can exploit that. Now that sounds kind of vague, but let me give you a concrete example here. So let's look at a 2-tap channel from a signal processing perspective, and suppose that our signal model is y of n equals h0 s of n plus h1 s of n minus 1 plus noise here. So we've looked at this channel a lot, right? Normally we have L, but I've just put L equals 1 here. So what you can see is that I've got 2 different channel realizations here, H0 and H1, right? H0 might correspond to this direct path, H1 might correspond to this reflected path. So if my direct path gets faded, I still have my second path here, and I get the information delayed. But that delay is not a problem because we're equalizing anyway here. The point is that in y of n, I'll see s of n. In y of n plus 1, I'll see s of n again because it's going to be delayed. So I see every symbol here twice. So the more multipaths I have, the more times I see that because of the memory in the channel. And so you can get some benefit from this if you can do something smart at the receiver here. So to exploit, you need a very good equalizer. Or better yet, something that's more sophisticated like maximum likelihood sequence detection. So I should probably put this like this here. Or you could also use OFDM plus coding and interleaving. Why this works is that, remember, this frequency diversity effect is going to create a channel that's frequency selective, and we're sending, information on these different discrete time subcarriers. And some of them will be fading and others won't. And just like with time diversity, if you have coding and interleaving, you can get some resilience to these deep fades here. And it's also why all OFDM systems have coding and interleaving built in, because you have to get resilience to this fading here. And if you have two taps here, there's going to be at least, this is a channel with 1, 0, and so there's going to be one point where the channel's fading. So this is actually quite a deep fade here. The more taps we have, the more variation we'll get and actually better performance. So that's how you can exploit frequency diversity here. Yeah. Okay, so to exploit this here, you need to have multipath. So you need to have lots of paths coming in with different time of arrivals here. So to exploit, you need to have enough delay spread. Right, equivalently, your power delay profile has to be spread out enough, and that's not always the case, because if you're in like a rural environment, there's not a lot of reflections, maybe you don't have many paths coming in. In this room here, we have a lot of paths coming in, but the maximum path time arrival difference is going to be, 30, 20 nanoseconds, so maybe not enough. So you need to be in an environment where you've got a lot of multipaths here. So again, not something that you can always rely on here. But what you can hopefully see here is that if you had coding and interleaving, and you do this over time, you can exploit time diversity when it's there, and you can exploit maybe frequency diversity when it's there. If you have an equalizer and you have coding and interleaving, you can get both. And so systems use multiple forms of diversity so that we can take advantage of one or the other when it's there. So those are the two most common. I have only a couple of minutes left here, so I'll mention this last one quickly here. But this one, actually, we're going to talk about a lot more in the next few lectures, so we'll discuss it much more. But this is called spatial diversity here. Spatial diversity is a little bit different because what we do is we suppose that, for example, at the receiver, instead of having one antenna, we also have a second antenna connected to our system here. And the spacing of these antennas is such that they're greater than the coherence distance. Now, we did not define the coherence distance before. It turns out to be intimately related to the coherence time, because coherence time is essentially coherence distance, in a sense divided out by how fast you could traverse that distance. So coherence distance, but it can be defined similarly here. And in typical systems, this is on the order of anywhere from a half a wavelength to 10 wavelengths. So half a wavelength would be on your handset in this room. 10 wavelengths would be for the base station antennas on top of the building here. And the idea with spatial diversity is just that you have multiple observations of the channel here. So you get to observe, so let's say, maybe this channel going to this antenna is H1, and if we space them far enough apart, this channel's H1 and H2 are decorrelated, and so we have two chances to decode the signal here. So you can imagine, we get something like Y1 equals H1 S of n plus V1 of n, and Y2 of n equals H2 S of n plus V2 of n here. So you have that same symbol with different noise in each observation here. The spatial diversity is also nice because it also gives you a bit of improvement over noise too. That we'll see when we do the exact calculations here. But essentially you need, to exploit this here, you need some form of array processing. So this could be some form of beamforming or space-time coding. You know, there might be some feedback involved, et cetera here. So we're going to talk, you know, a lot more about this here. And then as far as how you get it, you need, you know, multiple antennas. Not always possible, you know, to fit multiple antennas on a small device. But there's a little tricky way around this here, which is that you can also use multiple polarizations. And so you can build like a dual pole antenna from one piece of material. And so polarization is a special case here. So let me just put that down here. Polarization, special case. So to give you some ideas of numbers here, 802.11, actually even ABG had 2 antennas, access points and in devices. N has 2 or 3, sometimes 4. Cellular, most of your cell phones will have 1 or 2 antennas. The base stations have usually 4, 4 being 2 dual pole antennas, and they're going to 8. So these are kind of the numbers that you'll see here is on the order of 2 through 8. Now, in some of the research that we're doing, we're looking at hundreds of antennas, but you know, this is in what's deployed right now on the order of, you know, billion units around the world is typically 2, sometimes 3 or 4. All right, so that's diversity concept here. Now, just to go back here and summarize here, so you should be able to calculate the probability of error using this trick that we examined, and as well as perhaps calculating it for another kind of fading distribution, which would be, you know, kind of a fun problem, hint, hint. And then you should be able to describe some of these different sources of diversity and explain, at least on an intuitive level, why diversity seems attractive in fading channels. And we'll make that more precise in subsequent lectures here. All right, so that's it. Be in my office hours after this. If you have any further questions.